Welcome to Chapter 14, Chemicals, Pollution, and the Environment. This one is a bit of a doozy, so sit yourself down, get something to drink, and welcome yourself in. We'll start off by doing a quick demo about pollution and acid rain. Now, since I don't have matches handy, but I have homemade fireworks, I will use those instead. Today we're going to study pollution with our friend, the cabbage indicator. Please note the color of the indicator dyed on this paper towel. I'm going to now light a fireworks and see what pollution may be absorbed onto the paper towel. So, got a fuse going. Ooh, say that was successful. The paper towel is now incredibly pink, where that has burned pink as the sulfur compounds have burned and produced acid rain, changing the pH on that paper towel of the cabbage indicator. Now, we'll start off by just talking about the parts of the Earth that we're going to specifically talk about. We're going to talk about the lithosphere, which is our hard, rigid shell of our planet, the surface of which forms Earth's crust, which is 60 miles thick in some places. We'll talk about the hydrosphere, all the waters contained within the Earth's crust, whether they'll be oceans, rivers, lakes, or groundwater buried within the Earth's crust, and our atmosphere, which is the body of gases that surround the Earth. All together, these will be combined to be our environment. So we're not going to worry about the molten core. We're not really doing anything with that. It's the ground we stand on, the water we drink, the air we breathe. The crust is only about 0.3% of the mass of the Earth, and its thickness will vary between 8 kilometers under our ocean to about 45 kilometers beneath the continents. And the crust is mostly silicates, which is silicon and oxygen. As we can see on this chart, oxygen is the most abundant, 46, followed by silicon at 28 by weight, then aluminum, iron, calcium, sodium, magnesium, potassium, titanium, and hydrogen. Now, that's not to say there's not a ton of other metals in there. It's just they're too small to be a good percentage. You'll notice oxygen is also dominant in the oceans. That the next one, oxygen and hydrogen. Of course, most of it is water, H2O. And though if you predicted it by mass, you would say that oxygen should be closer to 88%, but it's a little lower due to due to soluble salts and organics. So we have like salts like chlorine and sodium. We got magnesium and sulfur and calcium and potassium, bromine, carbon, various other things. Again, too small. And of course, our gases, we have nitrogen and oxygen, the two major components, followed by argon, and then it gets into like smaller gases, CO2, neon, helium, methane, krypton, hydrogen, nitrogen dinitrogen oxide. So, now as we talk about pollution, it is a very charged word. Sometimes it's really hard to get it nailed down to what it actually is. Because, I mean, we could have contaminants in the water, which we set by the Safe Drinking Act and other laws. But it could be, pollution could be the limits of our physical detection. Can we sense the pollution there? Can you drink it and go, oh, that tastes a little funky? Can we see, should be pollution be with the limitations set by our federal government? Should pollution be set by how much causes a harmful effect, regardless of what the government says? So to get to a standard definition, we need to agree on some facts. So we're going to say pollution is when an excess of a substance, which must be generated by human activity, is present in the wrong environmental location. So this is not precise. It's not scientifically rigorous, but it's the definition we will work with. It's not saying that isn't bad things produced by the earth, like volcanic eruptions, but there's not much we can do about that. And it's not saying everything we produce chemically is bad. It's just saying that when we produce it, too much of it in the wrong place, it gets to the wrong place, that's when it suddenly becomes bad. We can look at, when we think about things, we need to think about the difference between purity and contaminated. When we say pure rainwater, it's not really pure. There's lots of dissolved gases, as we'll talk about later, like CO2. There's also various salts and little specks of dirt. Part of how rain forms is it coalesces over particulates in the air, and that it acts as a seed for which the water to form on and grow. So when farmers have someone seed the clouds to make it rain, they're essentially dumping a bunch of particulates into the air that thus causes the water to coalesce, and thus the rain clouds become too heavy and they fall to the earth. So carbonic acid, for example, there is no chemically pure natural water on Earth. Only pure water can come from a lab where we physically distill it and deionize it. We do everything in our process to remove all the other chemicals so that there's nothing dissolved in it. That's the only way we can get chemically pure water. Even then, it's odorless and tasteless, and it's not something we would really want to drink. Same thing, air can never be pure. Air is, as we saw, a mixture of gases with varying amounts of water, some occasional ozone due to lightning strikes and other natural phenomena. There's various volatile organics made by plants and animals that we can't really help. You got methane coming from cows, for example. You got various organics coming from trees like alpha pinene, that pine fresh scent. We talked about it being hazy in the distance. So if you look over a forest, that's that alpha pinene creating that effect on the light. So lots of organics that are going to go into the air that we can't really help. Environmental purity, when we talk about that, with air and water, we want air and water that's wholesome and pleasant to consume, that's free of disease-causing chemical and biological organisms. We don't want to hurt ourselves. To be considered pollution, it needs both substance and location. So ozone in the lower troposphere is not good. Ozone in the stratosphere, as we'll talk about later, is good. Ozone is an irritating toxic gas that will cause your lungs to inflame, but it will also be the life-saving shield that's going to protect us from ultraviolet rays. SO2, which we're going to talk about a lot, is going to form acid rain. However, we still use it in various chemical processes. So if we can collect it and prevent it from being released into the atmosphere, it is rather useful. So our definition specifies that it's anthropogenic, that it's not natural. It's not a volcano. It's not the pollution, like a forest fire by lightning would not be pollution. We can't really help that. That's part of the forest's natural process. However, wildfires sparked by human negligence would be forms of pollution. Now, Earth is about 3.5 to 4 billion years old, with life being about several million years old. We only have a very short time on Earth compared to the overall age. Animals have survived and adapted, and some of them have gone extinct naturally to various processes, whether it's been like the meteor causing the ice age, wiping out the dinosaurs. We've had various extinction level events. But the fact of the matter is they're finding it very difficult to survive due to the rapid increase of pollution. As we see here, that this chart from Science Advance is down here, that we look at the time period, the rate at which animals are going extinct. Whereas I think the A is the very conservative estimate versus B, which is the conservative estimate. Either way, you can see around 1800s, at least in this, since we started measuring this, see a sudden spike as all of them are going extinct very rapidly. Yet there's no extinction level event besides humanity. There's no meteor coming to strike the earth. There's no lava flowing over the earth. There's no floods. There's nothing more than what's normally happening. When we talk about pollution, yes, there is some natural pollution. Volcanoes dump a bunch of SO2. I mean, just thinking about the new Tonga volcano that's just been going off right recently. They dumped tons of CO2. In 1991, Mount Pinatubo released 15 to 20 million tons of SO2. And El Chicon in Mexico has released 7.5 to 10 million tons. So they're not always huge. Mount Kilauea is constantly releasing about 350,000 tons every year, and for multiple years, with a total of about 3.5 million tons per decade. Yet humans release about 20 million tons per year since 1950. So 90% of the SO2 in the atmosphere is from humans. Something like 151 million tons just in the 1980s alone. Though in 2000 we're down to about 97 million tons, if I'm reading my notes right. So if you look at this chart, this is the SO2, global SO2 release by world region by decade. So if you add them all up, 1850 is slowly increasing, peaking, and it's jumping way up in the 80s, though it's slowly dropped back down as we've tried to cap some of this off. But as it is, Asia is not really slowing down much. Africa is increasing a little, but not much. It's the Europe and the North America who are actively at least keeping it more or less constant or trying to go down. See, from here to there, we've tried to reduce. From here to try to reduce. The world consumes about 9 times 10 to the 16th kilocalories of energy per year, which at least that's what the book was talking about. However, I've looked it up. It's about 9.7 times 10 to the 16th now. So while we can burn petroleum produces CO2 and water, even in the best cases. Coal, natural gas, and petroleum are rarely just pure hydrocarbons. They often contain sulfur compounds, trace metals like nickel and vanadium. And while the sulfur content can vary from the source to less than 1% sulfur in oil wells like in Mississippi and Louisiana, to several percentages of sulfur in places like California and I think Wyoming. And the same can be true for coal. If you look at the different sources of coal, you can have relatively pure, very with various degrees of sulfur compounds, depending on whether it's like, say, Illinois coal or Pennsylvania coal. Basically, where the coal mine is, where's the thing. In petroleum, the sulfur often exists as organosulfur compounds, but in coal, it exists in iron pyrite, which is FeS2. Now, when we burn the iron pyrite, it's going to produce sulfur dioxide. Now, while we can process this and remove many of the impurities, but as the impurity increases, so does the cost to process it will increase exponentially. So if we try to get it perfectly pure, the cost is going to be too high to make it worth our while. So there's going to always be some degree of impurity in there. So we're going to burn some coal and we're going to get a little bit of sulfur dioxide. You burn the coal, you get some iron oxide, some rust essentially, and some sulfur dioxide. And that's going to enter the air as a primary air pollutant. And a primary air pollutant is a pollutant that enters the air as a direct result of a specific activity. So it's basically, it's the first contact pollutant with the air. Now, sulfur can undergo a variety of oxidation reactions. So sulfur dioxide can oxidize to sulfur trioxide, and then which is also a highly irritating gas and as low as 1 ppm concentrations. But this sulfur trioxide can also dissolve into water to form acid rain. The H2SO4 is sulfuric acid, very concentrated acid we use in the chemistry lab. These sulfur trioxide and sulfuric acid are examples of secondary air pollutants. They are pollutants formed by further reactions of the primary air pollutant. So it's a secondary effect you didn't really predict, you didn't really expect. When we talk about these guys, we can lump them all together in sulfur oxides, or SOX for simplicity. So SO with X, we don't know how many oxygens. There are many other pollutants besides just sulfur. We can form nitrogen oxides, NOx's, by the reaction of nitrogen at very high temperature. Now, nitrogen is usually very, very stable, but at high enough temperature, it will combust with air, with oxygen. Now, this can happen in lightning strikes. So whenever lightning happens, we naturally form NO, which is natural and thus not a pollutant. But it can also form in car engines, very high temperatures, because when we insert the air to burn the fuel, we're inserting oxygen and nitrogen. So it forms nitrogen oxide as a primary pollutant, but then it can undergo oxidation to form NO2, nitrogen dioxide, which is a red-brown gas that is a toxic irritant. At between 100 to 200 ppm, it can cause a fatal inflammation of the lungs. Now, while NO2 is not a major pollutant, it can undergo further reactions with water to form nitric acid, another type of acid rain. Also, when struck by high-intensity ultraviolet light, nitrogen dioxide can form, can break apart to form a molecular oxygen atom, which then can bombard itself with oxygen in the air to form ozone. So all these nitrogen oxides and ozone is responsible for the brown haze we often see above the city. This is responsible for our photochemical smog, which is just a complex combination of all the products resulting from the initial interaction of sunlight and nitrogen dioxide, and the subsequent reactions with bimolecular oxygen, as well as hydrocarbon pollutants. So all that smog is from our NO2s and our ozones and all the not healthy to breathe stuff that's in our atmosphere. And this becomes even more noticeable in the case of a thermal inversion. Normally, temperature goes down with altitude. So if you go higher up in the atmosphere, the temperature decreases. And hot air will naturally want to rise because hot air is less dense than cold air. So hot air will want to rise up to replace the colder air above it. So in the case of a thermal inversion, when a warm body of air moves in over top of a colder body of air, it will trap the colder, denser air below it. And any pollutants in that colder air get stuck there as well. So normally they would all rise up with the hot air and disperse into the atmosphere. But when you have a thermal inversion, there's the cold air, it becomes trapped, and so all the pollutants become trapped and it builds up over time. Now, there's other dangerous things like carbon monoxide, which is the colorless, odorless killer that can be formed by incomplete combustion of our hydrocarbons. Now, this is primarily in cities, but this can be formed in charcoal grills in an unventilated room. So never try to use a grill to heat up your dorm room or any other room in your house. As the oxygen runs low, you get this carbon monoxide, which in only small doses can kill you. That's why running a car in a closed garage is incredibly dangerous. It's often used as a method of suicide. So do not. It's not a pleasant way to go. Now, you often get some metals and organics. We release about 360 kilograms of mercury into the air per year just from dental fillings during cremation. So you cremate a body, any of his dental fillings has mercury in there, and then it volatilizes that, so we're releasing mercury in the atmosphere. It's not a really good thing to breathe. We also have things like volatile organic compounds and volatile organic solvents, VOCs and VOSs, that are just volatile organic compounds that can produce air pollution, like paint thinner, roofing tar, other petroleum distillates, various solvents and propellants, nail polish, aftershave, hairspray, insecticides. All these things that can go into the air and cause pollution and bad effects. Though the majority of our pollution still comes from fuel consumption in one way or another. So paint thinner does not provide a very large quantity of pollution, all said and done. Acid rain is one of the nastier effects of our pollution. This idea was coined in 1852 during the Industrial Revolution. This typically describes rain formed from SO3 and NO2 to form nitric acids and sulfuric acids. That this rain can kill vegetation and marine life. It will damage buildings and artwork and stonework, creating such nightmares like the picture we see up there. It used to be a beautiful sculpture, beautiful gargoyle, and now it's something you would not want to meet in a dark night. It destroys the features, especially limestone. Limestone, calcium carbonates. Carbonates are particularly reactive with acids. They will easily dissolve. But rain is naturally acidic from CO2 dissolving. When CO2 dissolves, it forms carbonic acid, making rain about 5.6 pH. Now, with other natural sulfides and nitrides in the soil, rain can drop to a pH of about 5, even in uncontaminated regions. So you get agrarian farmland, you can still have pH 5. However, pollution can lower that to between pH 4.1 and 2.0. Now, pH 5.6 is about the pH of milk or tomatoes. pH 2.4 is like vinegar. Milk, you don't really think of milk as being sour unless it spoils. Vinegar, I wouldn't suggest drinking that. Quick reminder, when we talk about pH, that's a logarithmic scale. Going from pH 2 to pH 5 may not seem like much, but that is an 1,000 increase in concentration. That's a increases in concentration by a factor of 1,000, not by 3. Now, because this is in the air, wind can carry this pollution from one country to another country. Just because you're making the pollution in China doesn't mean it stays there. It can go to Mongolia. It can go to Russia. It can cross the ocean, go into Hawaii. This becomes an international issue. Canada is often affected by acid rain in the US. Between affecting wildlife reproduction, like the acidity changes uh, killing them or speeding up the life cycles. It can make trees more susceptible to diseases, can destroy marble structures. Generally, it's a pretty big problem. Now, how can we try to reduce acid rain? We could switch to alternative energy. So try to generate energy that does not produce acid rain, that doesn't produce SO2s and NO2s. We can try to remove pollutants from the products of combustion. So after the fact, remove some of the pollutants. We can try to improve the efficiency of combustion so that we have to burn less fuel to get the same amount of energy. And maybe we'll produce less of the byproducts. And just energy conservation as a whole, where we just burn less. We burn less because we don't use as much energy. We don't waste the energy, so we don't have to burn as much. Things like methane has a lot less pollution due to lower sulfur impurities than natural gas. It will form, so thus it will form fewer sulfur and nitrogen oxide compounds. Now, electric cars and hydrogen gas would have no pollution, no direct pollution at the source. However, they do require energy to charge the battery or energy to form the hydrogen. So without a great solar or wind alternative power, we're simply transferring pollution from the vehicles to the energy factory. So instead of doing all the pollution in the city, maybe we'd be doing all the pollution like the next town over or in the country, wherever that factory is that's producing the energy that powers the car, the energy that splits the water. So by itself, electric cars are not perfect. Hydrogen fuel is not perfect. Even though hydrogen would burn to form just water, we need to form the hydrogen first. Now, as we think about cars actually only produce a small fraction of the SOx and NOx products in the US. I know we always see the smog in the city, but really the majority of the waste comes from power facilities and factories that are essentially stationary. They're not moving around. Now, because it's mostly coming from those guys with the big smokestacks, if we treat them, we're treating the majority of the source. Now, there's several methods of lowering the pollutants. One is electrostatic precipitation, one is filtration, and one is scrubbing. Now, the electrostatic precipitation, we remove the particulates, which are particles greater than 10 to the negative third millimeters, and the aerosols, which are particles smaller than 10 to the negative third millimeters. So basically, bigger than a micrometer, smaller than a micrometer, depends on how big the particles are. But so what happens? We run the gas in, we have an electrically charged center electrode. Now the electrons from there charge the solids and the aerosols, and they become attracted to the positively charged walls of this. As they're attracted, the unparticulated gases can pass through, the uncharged gases can pass through. So the liquids run to the sides and then run down to the bottom of the collection thing. The solids can stick to the side, and then you can use some agitation to shake them off so they sink to the bottom. But essentially, by charging the particles, they stick to the sides and stay there. The filtration, it's pretty simple. Filtration is the same way as you would filter air in your house. You have a little screen with tiny microscopic pores. The pores are a certain size category so that the air molecules, which are on the nanometer or smaller scale, can pass through. The aerosols, which are, as we saw, like micrometers scales, maybe get stuck in the holes and they cannot pass through. So the large particles will be stuck behind and the air can pass through safely. That's pretty straightforward. Now, the scrubbers are a little bit more interesting. So we pass air through this water misting system. As the gas gets sprayed, the water then absorbs onto the aerosols and the solids, and it's passed through a filter with a fine slurry of things like calcium carbonate or magnesium oxide. And then, so the absorbed water, sulfur dioxide, reacts with the slurry to get captured as various solid salts. So, like magnesium hydroxide goes to magnesium sulfite in water. Calcium carbonate and sulfur dioxide goes to calcium sulfite and CO2. So it releases some gas or some liquid behind. And one of the beauty of this is once we have the sulfites, we can change them back. We can change them back to calcium oxide or magnesium oxide and recapture the sulfur dioxide for use later. Ozone is another example of a helpful pollutant where location and concentration is very much so the key. In the troposphere, it is a toxic irritant, but in the stratosphere, it blocks the radiation. Ozone can be formed by lightning. It can also be from the sparking of a motor or electrical applications. So I've been told that model trains will actually, as they run, the little electric circuits in the model trains will generate ozone as well. Now, the generalized reaction is just three molecules of oxygen will form 2 molecules of ozone. How that actually happens is there's a slow first process of one oxygen colliding with another one to form molecular oxygen and ozone. And that molecular oxygen is very reactive, that once it bumps into oxygen, it then sticks to it and you form the second molecule of ozone. However, ozone in itself is highly unstable. So over time, it will break back down into the 3 oxygens again. It all depends on the concentration and the energy present. However, this can naturally form in the upper stratosphere. In this upper stratosphere, we have things like ultraviolet light will strike oxygen and split it into 2 molecular oxygens. While that could reform into O2, the likelihood of 2 molecular oxygens bumping into each other is highly unlikely. So it's more likely that one of the molecular oxygens will bump into O2, which is in much higher concentration, thus generating the ozone. Now, ozone in urban areas will peak during the day with intense traffic and tends to drop back down at night as the traffic diminishes and the ozone can thus start breaking back down. A little bit of ozone isn't bad. It adds a fresh quality to the air after a thunderstorm. But long-term inhalation of ozone between minutes to hours at concentrations as low as 1 ppm can lead to a sore throat and bronchial irritation, coughing, and fatigue. If you have much higher concentrations, ozone can even kill you. Ozone is not necessarily bad, even all things considered. We use ozone as a disinfectant for water because just like it's dangerous for us to breathe, it's dangerous for various microbes and bacteria, that it's highly reactive. So it can be used much like chlorine and bleach. By ozonolysis into the water, it can kill those. And in the stratospheres, that's where it's actually the most beneficial. Now, UV rays will promote vitamin D formation in our skin, but they can also destroy living cells. Sunburn is an example of the solar radiation destroying the living cells, and that's really painful and not really good. When our skin tans, when it darkens, that's our skin trying to protect itself from further radiation damage, saying darken so as to prevent the radiation. Now, long-term exposure to UV radiation can cause premature aging and skin cancer. And that's just from the weak UV rays that get through. Intense solar radiation would be lethal to all forms of life. Thankfully, are filtered out by the ozone layer. Picture there is of a truck driver, I think 69 years of age, who essentially half of his body was he's hanging his body out a window down. Half of his body was exposed to solar radiation more so than the rest of it, which was in the solar protected like cab. So half of his body, he's always driving on the right side of the road. So the left side of his face is always getting sun shining on it. So you can see he's far more aged on the left than he is on the right, just from excess UV radiation on the left of his face. But as I was saying, so ozone forms in the upper atmosphere. And once it's formed, it can then absorb more ultraviolet light and break back down into O2 and molecular oxygen, which molecular oxygen, very highly reactive. If it hit ozone, splits back into 2O2. If it hits another molecular oxygen, it goes into O2. But if it hits more oxygen, it can reform ozone again. And because of this, we have a cyclization process based on the concentration of those three gases. And ozone will be consumed and reformed over many thousands of years. We've reached a steady state concentration where ozone, with all the UV light coming in, it gets consumed and formed, and stays more or less at constant concentration. Since this has been a constant for many centuries, at least this has been until we introduce some highly volatile, relatively stable, halogenated organics. These great guys are great because they have very low toxicity, and low to non-existent flammability. We thought they were safe to use in our consumer products. They're not going to burn. They aren't toxic to humans. So we can use this. We have things like carbon tetrachloride, which is a cleaning fluid and flame retardant, essentially using a fire extinguisher to put out the fire. It really doesn't want to burn. Methyl bromide, which was a pesticide. I think chloroform, a solvent, and a raw material. Or no, that might be methyl trichloride or ethyl trichloride. We have various CFCs, chlorofluorocarbons, and hydrochlorofluorocarbons, like trichlorofluoromethane or dichlorofluoroethane, which are used in just about everything. They were used in aerosols for hairspray and various other sprays to help get the chemicals into the air. They were used in refrigerants. They were used as foaming agents and solvents. You could use it to dissolve the excess stuff in circuit boards. It's very useful, very useful. And things like halogens, which are polyhalogenated alkanes, like bromochloro-difluoromethane, also another flame retardant. Essentially, you can put out fire with this. All these were very safe until they weren't. They have since been banned or highly restricted because it's mainly because they're low reactivity and low water solubility, and they're very high volatility. Volatility is the ability to turn into a gas very easily. This leads to a very long lifetime in the atmosphere. While it takes 7 to 10 years for them to travel into the stratosphere, slow process to get up there, they can last there for decades or even more than a century in certain CFC cases. The basic idea is that high intensity light hits the chlorinated solvent just the same way as ozone. It breaks off a halogen like chlorine or bromine. We don't care about the other products. We care about the molecular chlorine or molecular bromine. Now, while ozone will naturally break down on its own, it's usually a relatively slow process. However, this will lead to a catalytic decay. A catalytic decay is one that lowers the energy of decomposition. So something occurs much faster. And because a catalyst doesn't get consumed and it gets reformed in the at the final step, it can go on to keep reacting. So ozone bumps into molecular chlorine. We strip off one of the oxygens to form just oxygen and chlorine monoxide. Then chlorine monoxide bumps into another ozone, and we form two molecules of oxygen, and we reform our the molecular chlorine or atomic chlorine again. And so it keeps going and it keeps going, and this can keep consuming the ozone. This ends up leading to a rapid depletion of our ozone. And when the ozone goes away faster than it can be reformed, this is kind of a problem. Now, this process was recognized in 1974 by Sherwood Rowland and Mario, I'd like to say Molarin, the top and middle pictures. They shared the 1995 Nobel Prize with Paul Crutzen, who showed in 1970 that nitrogen monoxide can do this decomposed ozone catalytically as well. Nitrogen monoxide can will essentially go to nitrogen dioxide and then back to nitrogen monoxide again. So we're essentially started noticing ozone holes where we're getting like a lot more ultraviolet rays than we should be. And we noticed one over the Arctic Circle, I think. In 1978, not long, so 4 years after the Nobel Prize, U.S. bans all CFCs as aerosols. A decade later, scientists study the proof that it is still shrinking. The ozone layer is still shrinking due to the halogens already there. It's one of those things of, well, the damage is already done, and it's really hard to get rid of it because they can hang around there for a really long time, freezing up. The ozone hole was developing over the Antarctic Circle, and it was especially bad in the fall. But in 1987, the Montreal Protocol would restrict CFCs and halocarbons completely. But some good news for a change. The ozone hole has since begun recovering as of 2019. As of 2019, it's the smallest it's been since it was first discovered in 1982, at least according to Wikipedia. And then they predict a full recovery of the ozone layer by 2075 if things keep going on the current rate. So it's slowly recovering, but it takes a while. So it's got to be careful what we do. Some damage may not be permanent, but some it's a little hard to come back from after the fact. We use pure water, the non-saline kind of water, for most of our activities. If you think about it, though, this pure water is relatively scarce compared to our salt water. The Earth's crust holds somewhere around 2 times 10 to the 21st kilograms of water, and over 70% of it's on the surface. We are only able to easily reach about 0.3% of the water. Now, while we use and largely return about 4,300 kilometers cubed of fresh water from our lakes, our rivers, and our streams, and our groundwater, while we use that much, there is still some that is wasted. Now, groundwater is just water within the Earth's crust, lying just below the surface. So it'd be the stuff we're going to get under the ground, our wells, our aquifers, we'll talk about a little bit later. Now, while we use a lot of it, only 67% of all freshwater usage is actually for irrigation. Our everyday humid uses by like just normal everyday life is only accounts for 10%. So a lot of it is going to watering our crops and growing our plants. Now, as we worry about water, water can suffer from four major types of pollution. We can have biological contamination, which is pollutions resulting from disease-causing microorganisms. Things like Legionnaire's disease, various different parasites can be in the water. So you drink it, and it's going to make you horribly, horribly ill. Now, we try to deal with this by using things like chlorine or ozone to kill the bacteria. We use filtration, various things to kill the microorganisms so people don't get sick. Now, some of the more insidious one is thermal pollution. Waste coolant will, when it's when the environmental harm comes from warming a body of water. So we discharge something, we use water that's not necessarily polluted, it's just warmer because we used it to cool something down, cooled an engine down, you cooled something down, and we discharge the hot water and it warms the body, the body of water. And what is that doing? Well, the body of water needs a certain temperature to survive. Essentially, oxygen solubility is proportional to temperature. As the temperature increases, the amount of oxygen dissolved in there decreases, thus potentially killing and suffocating marine life in the area. Because if the water's too hot, they can't breathe and they essentially die. Because too hot of air, too hot of water means no oxygen. Sedimentary pollution is pollution resulting from accumulation of suspended particles. Now, this is largely caused by runoff of insoluble organic and inorganic chemicals or directly out of wastewater. This can have multiple different effects. We can block sunlight, thus killing aquatic plants. It can carry other pollutants with them. But this is the largest type of pollutant. They can be filtered out. We can allow them to settle. We can coagulate these sediments using clumping agents like aluminum sulfates. But it's basically you have particulates that floating in the water. And chemical pollution, which is just pollution from harmful, undesirable chemicals. Now, this is one of the more subtle types. While thermal pollution doesn't affect the potability, and sediments are usually visible and can be filtered out. Biological, while you can't really see them easily, they can easily be killed by boiling the water or using the disinfectant. And if you get sick, they usually make themselves known right away. You get sick, you take this, someone dies, someone gets horribly ill after drinking the water. You're like, oh, we need to clean this water. Chemical pollution often takes a long time to be seen, usually not seen right away, and the effects can be relatively slow. Like lead poisoning, you don't notice it right away until the damage is done. It takes a while to get into the system and bind to the various things. And by that time, damage is often difficult to undo. But chemical pollution could be road salt. So we try to de-ice the road. When it rains, it washes that off and into the water. Agricultural runoff like fertilizers, pesticides, herbicides that can run off. Household products that we carelessly dumped. Toxic waste dumps and oil spills. Water gets in and runs out to other places. All these things are examples of ways we can accidentally pollute our groundwater. And not all pollution has to be dangerous to everything. Now, nitrates and phosphates, we talked about at least phosphates when we talked about surfactants. Things like fertilizers and detergents can actually be beneficial to aquatic plants. These are things that help them grow. Unfortunately, this can lead to rapid algae growth that can both blot out the sun and thus kill marine life and block oxygen exchange. Now, there's other ways this can happen, and such the red tide, which there's multiple different instances of that. Most recently, there's a red tide in Florida in 2021, 2017, 2018. Multiple instances of this in Gulf of Mexico in 2015, 2011. There's many other times, many other places, but this red tide, this red algae that forms through this process will actually produce neurotoxins that actually literally just murders the marine animals to death. They eat it and they die a horrible death, and you have basically zones of death in these bodies of water because of this horribly dangerous algae growth. This process is called eutrophication. It's a form of water pollution in which plants are well nourished by pollutants thrive at the expense of aquatic animals, coming from the Greek words well nourished. Now, some organic pollutants will also act as nourishment for oxygen consuming microorganisms. And this leads to various things like measurement of the biochemical oxygen demand, which is just how much oxygen is needed in the environment to support all the aquatic life. And since there's a limited amount of dissolved oxygen that could be in a body of water, this can lead to a dissolved oxygen deficit. So how much oxygen is in there versus how much is needed to keep all life alive. So if the microorganisms uses up all the oxygen, the aquatic life die unable to breathe. And so by measuring these BODs and DODs, you can actually determine whether there's pollutants there because, oh, there's a bunch of microorganisms that more than we normally expect. Normally, we have the limitations of the food is going to keep the microorganisms down to a manageable level, but too much, and suddenly we have dangerous levels and kill our aquatic life. Now, we have 3 times as much groundwater as we have above ground fresh water. So things like aquifers are kind of important. An aquifer is a large layer of porous rock that will hold our fresh water from which water can actually be drawn from wells. Now, these aquifers make up 97% of freshwater supplies. Some aquifers are known as fossil aquifers in that they're non-renewable resource. Water seeped into these aquifers thousands of years ago, and they're not getting replenished. Places like the desert, when this was once underwater, the aquifer ran into there. But now there's not really too much water source, so it's not really being replaced. Places like Northwest Texas, countries like Libya and Saudi Arabia have most of their water source being from these fossil aquifers. So when they're gone, they're gone. What are we going to do? I don't really know. So porous rock like limestone and clay and whatnot, where the water will seep in and kind of stick there. Many of the aquifers are rechargeable aquifers. Like in the book, they talk about Biscayne aquifer over in Biscayne Bay. Now, this allows water to seep in and out from the lakes, the rivers, and other water bodies, depending on the total groundwater abundance. So if it's particularly wet out there, very rainy, the water seeps into the aquifer and it gets stuck in there for a while, growing like a couple meters, a couple inches to a couple meters, depending on the aquifer, the concentration. When you have a drought and there's not as much water up there, the water seeps out of the aquifer and helps refresh the lakes and streams. So it all depends. However, when rains fall on the surface of our ground to refresh the aquifer, they can also contribute to chemical pollution from runoff. Thus, we need to limit the use of certain dangerous chemicals. Sometimes chemicals get in regardless of our efforts. Like you can spill some chemicals here or there. We have various things used in making polymers, like vinyl chloride on the left, which is used in making PVC, polyvinyl chloride, or vinylidene chloride on the right, used in making chemicals like polyvinylidene chloride, which is saran. These are carcinogens and can cause organ damage when drank. And so we have to clean them out of the aquifer. We can't just abandon our major source. One way to clean this is by a process called air stripping. This is kind of interesting thing. We run the contaminated water in these small little misting sprays, and we use like an air blower, kind of like an air dryer, to blow fresh air through the sprays. Now, the volatile organics, while they're stuck in the water right now, as the air blows on it, it helps them evaporate faster than the water. And so they evaporate out this top, going with the air. The water more or less sinks to the bottom, largely purified. While it wasn't perfect, it lowered the concentration of the vinyl chloride from 21 parts per billion to 0.03 parts per billion. And it lowered the vinylidene chloride from 5 parts per billion to 0.02 parts per billion, thus cleaning them up largely. Now, there's many different pesticides, which are another common contaminant. Things like insecticides. Early insecticides, we had arsenic, lead, and mercury, which were kind of poisonous to humans. So they'd sink into the plants and get into our food supply and kind of kill us. Not very good. So we try to look at more natural, a little bit less toxic ones like nicotine from tobacco and pyrothins, things from chrysanthemums. We got things like DDT in the upper corner. DDT was discovered in like 1874 in Germany. It wasn't used as an insecticide until 1939 by Paul Mueller in Switzerland. He would go on to win the 1948 Nobel Prize for that. We thought it was relatively safe, and it is to some extent. It was used in World War II to remove pests from soldiers. You'd spray a soldier down with that to get rid of his lice, and that. We thought it to be safe, but it's largely unreactive. It resists environmental degradation, so it has some problems. It has a great solubility in fats, so it like stick into cow milk, into body fat, and then can cause organ damage later on. One of the key problems, or when I remember hearing about this, is it weakens the eggshells of birds, and so like you would have bald eagles, it would get into force, and bald eagles would try to sit on their hatching nests to lay their eggs, and they'd crush their eggs. The shells would be so weak they'd just be brittle, and the birds trying to raise their babies would kill them accidentally. And what makes matters worse is the insects began developing resistance to it. So we would have to use more and more for it to work. So in 1962, Rachel Carson, as we see up there, published a book, Silent Spring, warning of the danger of this. And not long after that, U.S. restricted its use. Well, I think it took to 1973. But this almost led to the extinction of the bald eagle and the peregrine falcon, which have thus started to make a comeback. But we almost wiped out the American bald eagle, our national symbol. The worldwide ban has since been formalized since 2004, a year after this book started coming out. So we still produced it and sent it to other people for a long time, but it's since been banned worldwide. Now, there's newer insecticides that are actually far more toxic, but they decay at a much quicker rate into harmless fragments. So like, well, it's not going to hang around in the environment and thus kill as many people or be as much risk. Things like malathion and diazinon and parathion. But only malathion is still in use. Everything else has been banned. Like, ooh, still bad. So another one that doesn't seem as dangerous is juvenile growth hormone. It seems to be a safer method to stop the insects by stopping them from maturing into adults, and thus they're no longer capable of reproduction. I don't see anything horribly bad about that, but I'm not sure what that does to our bodies when we take that in. And despite all these insecticides, herbicides are even greater usage, and that like atrazine and glyphosate and paraquats, they often end up in our groundwater from agricultural runoff and much greater quantities than all the other pesticides combined. Though these guys like atrazine, I think in the bottom left, glyphosate in the middle, and paraquat on the right. Things like in 2012, atrazine manufacturer ended up paying $105 million in a class action settlement due to having to clean up contamination of their product. Glyphosate, more commonly known as Monsanto's Roundup, has been subject to numerous lawsuits and various bannings and phasing out worldwide due to the possible carcinogenic effects. So Monsanto's like, well, if you use this right, you're not going to get cancer. But, well, it's like, yeah, it's slowly being phased out, not quite phased out yet, but it's going there. And on the far right, paraquat, with its toxicity and link to Parkinson's disease, it is banned in the EU and restricted in the US, but it's largely still used in developing countries. So one of that key properties is it's the positive nitrogens make it highly oxidative and thus generalize killing all of plants that it comes into contact with. But so if it doesn't kill you or give you cancer, it can give you Parkinson's later on. So some of these guys kind of nasty. We got to try to avoid them getting in the stream. So it's all about being very careful when we applying this. Being very careful, like make sure it's not supposed to rain immediately afterwards. You want to wait. That's how it gets into streams. You apply it on the field, it then rains shortly afterwards. It's not really sunk in, and thus it can be carried into groundwater. All that was just the hydrosphere. So what about the lithosphere? Well, solid waste. Where does it go when we throw it away? The U.S. I've updated this a little bit from the book. The U.S. actually generates about 292.4 million tons a year, which is up to about 4.9 pounds per person per day, which is up from, like, I think he was saying 4 pounds per person per day. While on the plus side, 69 million is recycled, 25 million is composted, which is up to about 32% of that waste being kind of reused. And then another 17.7 million tons food reused in other ways. So that little peak here from 2017 to 2018 going up. Otherwise, it's been more or less constant waste production, but more of it's being recycled over time, which is good. In the 70s and 80s, we had a lot of waste, not a lot of recycling. Now it's a lot more recycling, still a lot of waste. Still a lot of waste. The majority of this, as we see, goes into a landfill one way or another. And landfill may be suitable for some waste, but is not necessarily suitable for all the waste. Some things can find its way into the groundwater after the fact. Like one of the common examples they use is motor oil. Motor oil will contaminate drinking water, but also contains trace amounts of metal and additives. So motor oil just essentially gets dirty as it's cleaning the engine. And the U.S. generates something like 1.3 billion gallons per year, and about 200 million of that is suspected to be improperly disposed of. According to sources, if you recycle that, about from every 1 gallon of motor oil, you can get about 2.5 quarts of re-refined oil that can be used. The rest of that can still be burned for energy. While that produces some pollution, you're still better than potentially contaminating the waste. So this re-refined motor oil can be created at very low cost and a lot lower cost than it take to reprocess new petroleum. and it uses far less new petroleum. And thus, we can make our petroleum stores go farther by just recycling the oil. But sometimes environmental damage operates on a scale, both time and quantity. While small amounts of damage rarely reach catastrophic proportions, and they don't always make the headlines. Sometimes they do, and it's really horrendous. There is one of the most famous cases is the mercury poison in Minamata Bay in Japan. Basically, metallic mercury sulfates were being dumped by the Chiso Corporation upstream from Minamata. And then as this traveled to the bay, it was then converted to organic mercury, methyl mercury, by the bacteria in the sediment. While the metallic mercury was a lot less dangerous, the organomercury was incredibly toxic, and it would then bioaccumulate in the fish, in the shellfish in the bay, which was the surrounding area's chief source of food. It led to the death of hundreds of people as it builds up, and they were trying to figure out what was going on. Led to what's called the dancing cat disease. The cats kind of went insane and ran into the ocean and died. Then it leads to because it took a lot less of the organomercury to kill the cats. But it leads to ataxia and numbness of the feet and the hands, muscle weakness, loss of peripheral vision at low amounts, and then eventually leads to insanity, paralysis, coma, and death. You can see one of the victims in the upper right, their hand kind of curled into a claw due to the disease. And this, for the longest time, they fought, saying, "Oh, no, can't be from us. Chiso Corporation can't be from us. It's not. We dump this methyl. We don't dump methyl mercury. We dump mercury sulfate." Not realizing that it took a while to prove that no, it is you. It's just getting converted along the way. You don't intend for this to happen, but you're causing it. I mean, we were very laissez-faire back in the day. We thought that storing and sealed drums and then just burying them was the common method of waste disposal in the 40s and 50s, leading to eventually the toxic waste dump known as the Love Canal in New York. It shortly became forgotten by the people that, oh, their dump was there, and so they built a community over top of it. And over time, the barrels started to leak. And in 1976, they started to leak from the corrosion. And the whole community had to be relocated in the 1980s. And the whole thing was declared a federal disaster area, a Superfund site, where it's like, yeah, we can't, the whole town is abandoned. It's just dangerous. It just leaked into everything. And yeah, bad stuff. And sometimes you can have horrible things like a factory explosion in 1984 in Bhopal, India. Released a cloud of 23,000 kilograms of methyl isocyanate. According to the book, killed about 2,000 people and injured about 20,000 within a few hours. Though some sources online saying within a few weeks, we're up to like 8,000 or more dead, with another 8,000 in like another couple months. Sometimes big accidents happen, or pollution happens, and it can cause serious effects. Though even small acts of pollution can cause some harm. The book finishes up by talking about environmental tobacco smoke, also known as passive smoking and secondhand smoke. That this can be dangerous, causing lung problems, cancer, heart disease, even in the people not smoking. I mean, people thought like, oh, it's like it's far diluted. How can it have all these negative effects? I mean, but really, you're just pumping out various different particulates into the air that also contain carcinogens. You produce a wide variety of carcinogens that can have an effect, even though you're breathing some into your lungs as a smoker. You're pumping out others into the air that people can breathe in and still hurt us. But the question is, can we prevent all pollution? And is all pollution bad? You think about fluoridation. Fluoridation, as much as 1 ppm, can reduce tooth decay in kids. However, it doesn't seem to have an effect on tooth decay in adults. So there is no easy answer to this. Can we tell places like India and China they're not allowed to industrialize because we can't allow them to produce more pollution? Can we return to the medieval agrarian society and thus reduce pollution even further? Well, all we can do is be careful and try to reduce what damage we do. Try to lower the pollution and just be a little bit more careful as we go through. Now, pollution is a little bit of a tricky topic. As we defined it in this chapter, it's human-made pollution we're looking at. That it's usually in excess, and it's usually in the wrong environment. That idea that an excess human byproduct in the wrong environment is what we're going to define as pollution. Because otherwise, if you want to call it like aerosols as pollution, aerosols meaning like gases or chemicals sprayed into the air. Pine trees create aerosols. If you've ever seen a pine forest, you look into the air above the trees on like a mountaintop, it's very hazy. That's due to alpha pinols and various other terpenes and complex molecules that make that delicious pine tree scent you might smell. So, but that's produced not by humans, and that is naturally occurring within that area. There's not, the only way to get rid of that is cutting down those trees, and I don't think that's exactly what we're going for. That sometimes humans produce things, but if it's not in excess and it's not really harming the environment, it's like, oh, a little bit of heat there, a little bit of heat there isn't really going to be much pollution. But we're looking here that such pollution like, for example, phosphates or organophosphates in the detergent chapter, in the surfactant chapter, that they can create like mold, or not mold, but algae blooms, and that can kill large swaths of aquatic life. Now they have some issues with that down in Florida. That this is not supposed to be there, and that pollution then causes problems down the line. And pollution is a issue we want to deal with. I mean, we like our life, we like our standard of living, but it's an issue we have to deal with. I mean, people who fight for the Keystone Pipeline, like, we need this energy, and it's making jobs, and it's keeping the oil from from America in America. But you have situations like where the pipeline spills, and suddenly you have water and soil contaminated with this oil. We need to be careful to try to, well, minimize our damage. Once again, science, while it will often improve our lives, if we're not careful, and as a human, we are rarely, if ever, very careful about these things. If we're not careful, it will then cause more problems for us to fix. Hey, it's creating more jobs, but, you know, this old saying, the stitch in time saves 9, that fixing the problem before it's a problem will prevent 9 times the amount of work. And for people who want fiscal responsibility, saving 9 times the work is the responsible thing to do. So we need to think about our actions, and we need to show tremendous amount of foresight and try to take precautions and fail safes, things that keep us safe in the long run. As we'll move on in a chapter or two, we'll look at some toxins, we'll look at some polymers, and discuss the issues of those. But for right now, we'll leave you for now.